So we'll start the exercises for chapter 5 now. Remember that we talk about analog transmission or broadband transmission. So in that case, we tend to use the case factor. So remember, one common theme here is that the case factor equals to 1 all the time, which means that the signal rate equals to the bandwidth equals to n times 1 over r. So this is one common theme in this chapter. All right, so calculate the baud rate or the signal rate that given bit rate and the type of modulation. So for FSK, so for the case A, FSK with a bit rate of 2000 bits per second. So the signal rate equals to n times 1 over r, and for FSK r is equal to, remember, r is the number of bit element divided by the number of signal elements, and here it's still 1, so it's so S equals to, so S is 2000 baud. Remember, the unit for the signal rate is baud. So for B, S equals to n times 1 over 4, and for ASK again r is 1, so that's again 4000 baud. So for C, S equals n times 1 over r, and r here, remember that r here is for QPSK. For QPSK, each 2 bits are represented by 1 signal element, so R is 2, so that's 6000 times 1 over 2, so that's 3000 baud. For D, S equals to n times 1 over R, so that's for 64 QAM. So remember, R equals to the number of signal levels log 2 of L. So for 64, that's 6, which means that each 6 bits are represented by 1 signal elements. So S equals to 36,000 bits per second multiplied by 1 over 6, so that's 6000 baud. Okay, next exercise. Draw the constellation diagram for the following. For ASK with peak amplitude values of 1 and 3. So remember here that for the constellation diagram, each symbol or each signal representation is represented by 1 single dot in the IQ diagram. So this is the I component and this is the Q component. So the I, or the in phase, and the quadrature phase. So for ASK, we know that the phase shift is always 0, which means that we are always in the x-axis. So we have 2 representations, one with a value of 1, so this is here with one symbol, and one with for positive 3. So we have 2 dots that look like this. So we have 2 dots, 1 and 3. For case B, we have BPSK with a peak amplitude of 2. Remember, for BPSK we have 2 signal representations, one for 1 and one for 0, and for 1 we have positive 2, and for 0 we have negative 2. So this is positive 2 and negative 2. So this is for BPSK. For QPSK we have 4 symbols with a peak amplitude of 3. So you can do that using 2 types. Either we start from a phase shift of 0, or we start from a phase shift of 45 degrees. I select to start from like what we have explained in class. So we start from 45 degrees, and this is 3. So this is one symbol with an amplitude of positive 3, and we have another one here and one here. Okay, so for case D we have 8 QAM with 2 different peak amplitudes. So 8 QAM that's composed of 2 QPSK, one at 1 and one at 3. So we have one dot here and one dot here. We have one dot here and one dot here, and same thing here, here. So for this we have here this is positive 1 and positive 3, and this is 1 3 1 3 and so on. So we have 8 different symbols for so this is for 8 1. This is for Q P SK. This is for ASK. This is for B PSK. Next, so how many bits per baud can we send? Bits per baud, which means R, we send in each of the following cases if the signal constellation has one of the following number of points. So if we have 2, which means that binary, so in that case, how many bits can we represent per baud? We can represent, of course, R here equals to log 2 of the number of levels, or the number of constellation levels. So if the constellation level is 2, so R is 1, which is the number of bits per baud. So for the case B, R is log 2 of 4, that's 2 bits per baud, or per signal. For 16, R is 4 bits per baud, and for 1024, R is 10 bits per baud. Okay. Alright, so next exercise. What is the required bandwidth for the following cases if we need to send 4000 dBs? So let D equals to 1. Of course, D equals to 1 for FSK and QPSK is kind of unrealistic. However, we will take what the exercise says. So, what is the required bandwidth? So we know that the bandwidth equals, for ASK, bandwidth is equal to the signal rate, assuming that for ASK D is 0, so which is the N times 1 over R, which is 4000 bits per second, times 1 over 1, which is 4 hertz, 4000 hertz. For the case of B, for FSK with 2 delta F equals 2, so remember for FSK we have 2 symbols with a distance here which is 2 delta F. So this is for 0 and this is for 1. So the bandwidth equals to, 1 plus D times S plus 2 delta F. So bandwidth equals to 2 times S is N times 1 over R, and R is 1, plus 4000 or 4 kilohertz. So this is equal to 2 times 4000 plus 4000, so that's 12,000 4,000 hertz or 12 kilohertz. Okay, so for C, the bandwidth for QPSK, the bandwidth is 1 plus D times S. There's no 2 delta F in that case, so this is 2, because D is 1, times N times 1 over R. R here, remember that R for QPSK is 2, because we have each 2 data elements represented by one signal element. So R is 2. So we have 2 times N is 4,000 times 1 over 2. So that's 4,000 hertz. And for the case D, for the 16 QAM, again B is equal to 1 plus D times S. That's 2 times N times R. R is here is log 2 of 16, that's 4. So R is 1 over 4. So that's equal to 2 times 4,000 times 1 over 4. So that's 2,000 hertz. We have a corporation has a medium with 1 megahertz bandwidth. The corporation needs to create 10 separate independent channels within that bandwidth. So if we were to draw the spectrum for these 10 channels, so we have 10 channels that look like this, and all of them, they take 1 megahertz. So what is the bandwidth of each channel in that case? So for each channel, bandwidth per channel equals to 1 divided by 10, which is 10 kilohertz. So this 10 kilohertz, the company has decided that to use QAM technology such that each of these will have to support sending 1 megabits per second. So this bandwidth is required for sending 1 megabits per second. So if we know that this bandwidth equals to 1 plus D times S, and S is N times 1 over 4. So here the D value is 0, so this is N, and N here is 1 megabits per second, so 1 times 10 to the power 6 times 1 over R. So for QAM, we don't know the number of levels or the number of symbols that's used for QAM, and this is the missing part. So here the bandwidth per channel is 100 kilohertz, so 100 times 10 to the power 3 equals 10 to the power 6 times 1 over R. So obviously R here equals 10 to the power 6 divided by 10 to the power 5, so that's 10. So if the R value is 10, what is the number of levels we need? So obviously L equals, of course, we know that log 2 of L equals to R, so this leads to the fact that R is 2 to the power 10, so that's 1024. So we need 1024 QAM for this company. So if the company uses 1024 QAM for QAM modulation, then we can support the 1 mega bits per second for each channel for 10 channels. The last exercise is for analog modulation. So the exercise asks to find the bandwidth for the following situations if we need to modulate a 5 kilohertz voice. So remember, for analog modulation, the signal is characterized not by the bit rate or by the signal rate, it's characterized by the bandwidth itself of this analog signal. And as we have discussed in class, for the case of AM, the average bandwidth is 2 the bandwidth of the signal, which in that case is 10 kilohertz. For phase modulation, however, for the case of phase modulation, however, the bandwidth equals to 1 plus beta times the bandwidth of the signal. So this is 2 times 6 times 5 times 10 to the power 3, so that's 60 kilohertz. So for the last case, case C, the bandwidth is 2 times 1 plus beta times the bandwidth, so that's 2 times 2 times 5 times 10 to the power 3, so that's 20 kilohertz. So that concludes this set of exercises. And one last advice here is to try to practice these exercises a lot and go through the homework and try to solve all the problems, and do not get confused between the different equations in each part. Thank you very much, and Assalamu alaikum wa rahmatullah.